Hello everyone, today in this video we'll be discussing the fourth module of 21PHY12 and there are four main topics: classical free electron theory, quantum free electron theory, physics of semiconductor and dielectrics. Okay, so the derivations are in like I guess in this one and this one. So there are like total 5 derivations which are very important from exam point of view. So let's get started with the module 4. And before starting, if you like this video, hit the like button and don't forget to subscribe to my channel. So the first topic is classical free electron theory. So we'll be discussing what are the assumptions of it and what are the drawbacks. Then those drawbacks are overcome by the quantum free electron theory. Okay, so let's see what are the assumptions of classical free electron theory. The metal consists of free electrons. The current flowing through a metal is due to drift velocity of the electrons. Okay, this is the first assumption, and the energy associated with each electron is 3/2 kT is equal to half mv square. Okay. So what are the drawbacks? The drawbacks is the first one is the specific heat. There are 3 drawbacks in total. Okay, first one is the specific heat. So the molar specific heat of a gas is at the constant volume is Cv is equal to 3/2 R. Okay, but experimentally it was found that Cv is equal to 10 power minus 4 RT. So these two values don't match. So that was the first drawback. The second is the temperature dependence on electrical conductivity. It is experimentally determined that the electrical conductivity inversely proportional to 1 by T, but according to classical free electron theory it is 1 by root T. So those two are contradictory. Okay, that was the second drawback. And third one is that the electrical conductivity depends on electron concentration. Okay, so if it depends on electron concentration, and the electrical conductivities are 5.88 and 3.65, but the actual values are 8.45 and 18.06. So they are very much differing, right? So and the powers are also differing very much, right? So those are the 3 drawbacks of the classical free electron theory. Okay, let's move on to the next topic, which is the quantum free electron theory. So in the quantum free electron theory, the main thing is that the energy values are quantized in the conduction of electrons. So each of the electrons are present in energy bands which are quantized. Quantized means what? Nth value is equal to 1, 2, 3, 4 like that. Okay, no decimal values, only quantum values. The highest energy level is called the Fermi level, and that energy is called Fermi energy. And what about Fermi direct statistics is that it gives us the probability of finding an electron in the given region calculated using a Fermi factor. So Fermi factor's formula is this one. Fermi factor is equal to 1 by e power e minus ef by kt plus 1. Okay, that's the Fermi factor. Now there are 3 conditions when t is equal to 0k, t is less than 0k, t is greater than 0k. At these 3 conditions we will find what is the value of Fermi electron. Okay, so Fermi factor at t is equal to 0k, E is less than Fermi energy. At that time what happens, if E is less than Fermi energy, very less than that, so it will become e power minus infinity, that is nothing but 0 plus 1, and numerator also we have 1, so the answer is 1. Fe is equal to 1 means it's like 100%, right? The energy state is 100% if E is less than Ef. If it's greater than EF, at that time we'll get as 0 if you apply the same things here, and that shows that the probability occupation of the energy state is 0%. So that's what it is depicted here. At t is equal to 0k it is 1, at t is greater than 0k it is 0, and in between what happens, let's see that. That's the third case. Okay, in the third case it is approximately equal. At that time we'll get as 1 by 2, and that is 50%. So here 50% it will be there in the left region and 50% in the right region. Okay, here and here. And yeah, that's all about the 3 conditions of the Fermi energy, that is known as Fermi direct statistics. Okay, now we will be deriving an expression for Fermi energy at absolute 0 temperature. So according to Fermi direct statistics, this is the formula. N is the probability of finding Ge and Fe. Okay, the number of free electrons distributed per unit volume of the material up to Fermi level is given by the integration of Ne. Ne is nothing but GFE, so we are writing GFE here, and then we are integrating it. E is equal to 0 to E is equal to F naught. That's the limits, and Fe is equal to 1 at T is equal to 0k. So Fe's value becomes 1, and G is nothing but it's given by 8 pi root 2 m raised to 3/2 by h cube into e power 1 by 2. So we'll be substituting that and taking out the constants here, and then we'll be differentiating this, means integrating this one. So we'll get this answer, and applying the limits, finally we get this answer. Okay, so that is the value of Fermi energy. Okay, now merits of quantum free electron theory are like what were the drawbacks previously that are overcome. Okay, so the specific heat's value is given by this one according to quantum free theory, and considering the means what are the values for each of these terms here, that is close to 10 power minus 4. So the first contradiction is overcome. The second one, the temperature depends on electrical conductivity inversely. Okay, so according to the quantum field theory, this is the formula, and here what we have lambda, and lambda is nothing but 1 by pi r square, and r square is directly proportional to t. So what we get is, instead of this I can write as t, lambda is inversely proportional to t, lambda is proportional to this one. So obviously this one is electrical conductivity is inversely proportional to t. So that also proves the second contradiction. And third one is electrical conductivity and electron concentration. Okay. Here aluminum and gallium, which have 3 free electrons per atom, have lower electrical conductivity than that of copper and silver, which have only 1 free electron per atom. And it is observed that it satisfies the direct proportionality of the electrical conductivity and electron concentration. Okay, because it's directly proportional. Okay, and the values also which are obtained are close enough. Okay, so this also proves the third contradiction. Okay, so these three are the merits of quantum free electron theory. Okay. Coming to next topic, which is physics of semiconductors. Here what we have is the 3 to 4 very important derivations. So let's get started with the first one: concentration of electrons and holes in the intrinsic semiconductors. Okay, concentration of electrons and holes. Okay, these two concentration we are trying to find out. So the number of electrons in the conduction band per unit volume of the material is called electron concentration. Okay, how many electrons are present in a conduction band is called the electron concentration. Okay, and the formula is this one, and the things which are mentioned is given here. Okay, similarly the number of holes in the valence electron are this one. Okay, so it is given by nh and it is given by nc. Okay, number of electrons and number of holes, and these two formulas are very important. We'll be using in the derivations. The only difference between these two formulas is here it is minus ef in the number of holes, and here it is ef minus eg. Okay, that's the only difference. So let's move on to the derivations part. The relation between the Fermi and energy and the energy gap in an intrinsic semiconductor. This is the first derivation. So here what you have to find out is the relation between Fermi energy and the energy gap. Fermi energy and energy gap. For an intrinsic semiconductor, the number of electrons in a conduction band is equal to the number of holes in the valence band. Okay, so this is the conduction band C and this is the valence band V. So how many holes are present here? That is equal to the number of electrons present here. Okay, in the conduction band and in the valence band. So an E is equal to NH, the number is equal, and this is the formulas which we will be writing. NC's formula we will be writing here, and NH formula will be writing here, and equating them because both are equal, right? So when we equate them and simplify, what we obtain is this one. This equation we obtain taking log on both sides, we obtain this one, and then simplifying we'll obtain here. This is the final equation, and the me is equal to mh, the mass of electron is equal to the mass of holes, and L1 is equal to 0, natural log of 1 is equal to 0. So therefore what you get is EF is equal to Eg by 2. Eg is the gap, energy gap, and EF is the Fermi energy. So what we get is the Fermi energy is nothing but electron gap by 2. So where does Fermi energy lie? It lies in the mid part of it. Okay, if this is the conduction band and this is the valence band, Fermi energy lies here. Okay. The next derivation is the expression for electrical conductivity of semiconductor materials. Electrical conductivity is expression we have to find out. So if this is the means the wire here, in the wire the diameter is this one, and means the current is flowing here, and Vd is the drift velocity, means with the velocity with which the electrons are moving, and E naught is the energy gap. Okay. So what we are trying to prove is that the first thing is we have to find out the electrical conductivity's expression. So first we will write the current flowing is I, which is equal to NEA VD. Okay, and here the terms you already know, like N is the number of electrons, E is the electronic charge, A is the area of the means the wires, this one circles area, Vd is the drift velocity. Okay, and N is equal to Nc, the concentration of the charge carriers, which is the electrons, and current density is Jc, which is given by NCEVD, and J is equal to I by A. So A gets cut from here. Okay, A gets cut from here. Then the quantity Vd by E is a constant for particular type of charge carriers, and it's called the mobility of the charges. Vd by E is nothing but the mobility of the charges, and Vd is equal to Uc into E in the above equation. If we just cross multiply it and apply in the above equation, what we get is this one. So here if we apply the value of Vd which you got here UCE, and we will get here UCE. Okay, and what is NCE? NCE is nothing but sigma, and sigma is if we just means take this in the denominator, we will get Jc by E. Okay, till now we got the value of sigma c. Now we will be applying like sigma c is equal to NCE UC. So how we got this one is because of this one. See, in the place of this what we substituted, this one. So here what we can write is NCEUC is equal to JC by E, right? So equation 5 represents the conductivity due to the electron in the conduction band. This is the final equation which we want. But due to holes also we have to find out this just due to electrons. So for holes also we will do the same thing. Holes is equal to NHEUH. Okay, instead of C we will have H here. Now the total conductivity is nothing but means sigma C plus sigma H. Okay, and we apply these two formulas which you got in the above and here, and we'll take common what is their common here, and the final answer which you get is this one. And then since NC is equal to NH, we can apply that here as well, and we can take it as NI as common. So Ni will be outside and Ni will be outside, and inside the brackets will have nu E plus nu H. Okay, and that is the expression for conductivity in the intrinsic semiconductor. Moving on to the very next very important topic, which is the Hall effect, and it has three derivations. Okay, so we'll be starting with what is the Hall effect by the diagrammatic representation. So see here, here there are three things. Okay, here the first thing is that the Hall voltage is applied in this direction and the current is flowing in this direction. Okay, so these two are perpendicular. If you do this in this way, at that time the magnetic field will be produced perpendicular to the plane of these both. Okay, so that's what the basically the Hall effect says, and this phenomenon is known as Hall effect. Okay, so expression for Hall coefficient and Hall voltage, two derivations are there. For first is for Hall voltage and second is for Hall coefficient. Okay, so here as you can see there are three dimension. The first dimension, here the current is flowing, and here the magnetic field is coming, and the V is this one. Okay, V will be flowing this one voltage. Okay, and after making this one you have to write two formulas according to Lorentz force. At that time minus B E into V. Okay, this is the formula for Lorentz force. Second is the upward force driven by the Hall field, which is FH is equal to minus E into EH. Okay, equating these both we get minus EEH is equal to BEVD. Okay, now what we will be doing is we will be cancelling the E here and the negative terms here. So what we obtain is EH is equal to B into VD. Okay, if D is the distance between the upper and the lower surface, then EH is equal to VH by D. Okay, so VH will be equal to EHD, and applying that formula here, VH will be equal to B into VD into D. Okay, because EH is nothing but BVD, so here the D comes here, and VH is as same as previous one. Okay, and J is equal to I by A, and that is equal to NEVD, that is equal to P into VD. P is nothing but NE. Okay, so for the given semiconductor, J is equal to I by A, I is equal to I will be kept as same. A is equal to W into D. Okay, W is the width and D is the distance. Okay, so in that way we will get the area. So I by A, and W is the thickness, and A is equal to WD. Okay, so we get PVD is equal to I by WD. PVD how we got? By this one. J is equal to I by A, that is equal to PVD, and we'll be equating these both. These both equation when we equate, we'll get this one, and from here we'll get the value of VD. After we get the value of VD, we'll be substituting that in the formula of VH, which is in equation 4. So we'll get BI by PW. So P will be equal to BI by VHW. P is the coefficient of voltage. Okay, sorry, VH is the coefficient of Hall voltage. Now coming to the expression for Hall coefficient, since EH is directly proportional to JB, EH will be equal to RH JB. RH will be equal to EH by JB, and EH is nothing but BHVD, and JB is nothing but PVD into B. So that we will get as 1 by P, which is nothing but 1 by NE. RH is equal to 1 by NE is the equation for the Hall coefficient. Expression for Hall voltage, this is the expression for Hall voltage. After we get this one here, RH is equal to 1 by P into NE. At that time we can substitute that in this formula as P value here. When you substitute that in the P value here, we'll get this equation. This expression represents the Hall voltage. So those were the derivations important in the physical semiconductors. Okay, so this is the last topic, which is dielectric materials. Here two important derivations are there. So the first one is about the before that we have to see some basics here. These are the insulators, which are the dielectric materials. They are the insulators which get polarized when electricity is passed through them. Okay, so this is the dipole moment is equal to Q into I. Q is the charge, I is the current which is passing. So there are few types of polarization. Electronic polarization means if this is electric field is 0, positive is here, all negative are there. If electron field is greater than 0, I plus positive will come here, negative will come here. That polarization is known as electronic polarization. Ionic polarization means the plus and minus will come together and the lone will be set aside. Okay, so that is the ionic polarization. And the oriental polarization means if the directions are different in the presence of electric field, it will be directed towards the same direction. Okay, So these were the types of polarization, and the relation between the polarization and dielectric constant is as follows. Polarization is represented as P, and this is the dielectric constant for default medium, and this for the relative medium. So it will be equal to E naught into ER minus 1 into E. Okay. And there is a small theoretical concept which is internal fields in solids. So when dielectric material is subjected to an electric field, each atom develops a dipole moment. So when there is a dielectric material, if it is subject to electric field here, each atom here will be developing a dipole moment known as electric dipole. Okay. So EI will be equal to E applied plus E dipole, that is equal to E plus V by E naught P, and if it's a 3D surface, at that time the value will be P by 3 E naught. Okay. This is the important derivation under this topic, which is Calusius Mossotti equation. So here the first thing you want to write is a dipole moment per unit volume is equal to n into nu. The force experienced by atom is an internal field I is directly proportional to E, and the electronic polarization of their atoms. So it will be dipole moment per unit volume will be n alpha E into I. Okay, n into nu is nothing but this one. So nu's value is alpha into EI. Okay, that is the dipole moment's value. The dipole moment per unit volume is nothing but the polarization. So P will be equal to this one, and EI will be equal to this one. So also we have the value of P as the previous one, like E naught into ER minus 1 into E. So that we will substitute here as P. So what we get is this equation, and for the whole equation, like EI is equal to E plus P by 3 E naught, we will be substituting the value of P here. So what answer we get is this one. After we simplify these things, we will get ER minus 1 by ER plus 2 is equal to n alpha E by 3 epsilon naught. This is called the Calusius-Mossotti equation. Okay, so these are the most important things in the module 4 of 21PHY12, and thank you so much for watching. I will see you in the next one.